Okay, welcome to another fabulous day in Calculus 3. Today we're going to do implicit differentiation. Yes, indeedy. So what is it? Well, you're going to find derivatives where the function that you're given is given implicitly. So what does that mean? So let's do some Calc 1 review. When you were in Calc 1, you were given a function implicitly. This is an example right here. What do you mean? Well, usually when you're given a function, you're given like y equals f of x. And that is known as an explicit function of x. And when you have an explicit function of x, you know from Calculus 1, it was pretty easy if somebody goes, hey, go get the slope of the tangent line. You went, hey, no problem. Y prime is equal to f prime of x. And this was the slope of a tangent line to your graph. And you were like, hey, what's the problem? No problem there. But what if you were given a function of x implicitly? So sometimes when you're given an implicit function, you can get lucky and solve it for y, and get y on one side isolated and all the other junk on the other side of the equation, and get it to look explicit if it's kind of an easy equation where you can solve for y. But this is pretty hard. Like you probably, if you know how to work with cubics, and I don't want to get into it, there's a really nasty way that you could work this equation where you could finally solve for y and then get y equals and so on, but it's hard. And the reason why it's hard is because here you have y cubed, and you also have y squared, and then you also have y showing up right there, and ooh, it's showing up again right there. Oh my God. So it's better if you just leave it in implicit form, and then to get your derivative dy dx, you use this strategy that you used in Calculus 1, known as implicit differentiation. So how do you get the dy dx? Well, step one, this is a Calc 1 thing. You take d dx of both sides of the equation. What does that mean? You take the derivative with respect to x of the left-hand side, and that better be equal to the derivative with respect to x of the right-hand side. But when you do this, you have to remember that y is a function of x. And when you take his derivative with respect to x, you have to use the chain rule and take the derivative of his insides also. Well, what the hell am I talking about? Well, let's just do the problem the Calculus 1 way. So here I go. The derivative of y cubed with respect to x is 3y squared times the derivative of y with respect to x, dy dx. That's the chain rule in action. Plus the derivative of y squared is 2y times the derivative of y with respect to x. Plus, now this is going to be a hard one. This 4xy, ooh, you're going to need the product rule on that. Because it's a product of 4x times y. So let's take the derivative of 4x with respect to x, and that's just a 4. And then you multiply that by y. I'm using the product rule right now. Plus the derivative of y with respect to x, that's just dy dx, times the 4x. Okay. And there, I'm done with that term. I use the product rule. Equals, now let's do the right-hand side. Well, the derivative of 1 with respect to x is 0, so I won't bother. The derivative of 5y with respect to x is 5 times the derivative of y with respect to x, dy dx. And then minus the derivative of x squared with respect to x is just 2x. Now notice I'm not using partial derivatives here at all, because Calculus 1 people don't know how to do partial derivatives, okay? Of course not. Now, what did a Calculus 1 student do? Step 2 for Calc 1 is get all dy dx terms on one side of the equation, and then you can put everybody else on the other. Now, it doesn't matter which side of the equation. You get to pick it. How many dy dx terms do I have? Let me just count them up. Ooh, 1, 2, 3, 4. Ah, man. How about if I move all of them to the left side? Because most of them are already on the left side anyways. So if I want to move this one guy on the right to the left, I'll just subtract 5 dy dx from both sides. Now this term here, we'll move it to the other side by subtracting 4y from both sides. Okay, fine. What happens after I do all this moving? Not much. So this is what happens after I move some folks around. Now what? Step 3, factor and solve for dy dx, and then you're done. This is what a Calculus 1 student did. And yes, this is a pain in the butt behind. I won't lie. So on the left-hand side, notice that dy dx is a common factor. Aha. And if I factor him out from those terms, the other factor is going to be this big old expression, 3y squared plus 2y plus 4x minus 5. Ugh. And that's still equal to the right-hand side, which is negative 2x minus 4y. And then the very last step is just divide both sides of the equation by that big old expression, 3y squared plus 2y plus 4x minus 5. And I'm done. And I have the derivative of y with respect to x, which would be giving me the slope of a tangent line to this curve for this implicit function of x. And there would be the formula for the slope of a tangent line. Okay, so hopefully you remember a little bit of this when you took your Calc 1 class. Now, just for kicks and giggles, I'd like to graph this implicit function of x. You can't really use your calculator to graph it. Well, why not? Well, because your calculator, your graphing calculator, that is only good for explicit functions of x, you know, and this one isn't. So like, just what would the graph look like? I'm just curious. I don't remember. Heck. Let's have some fun and see what the heck this curve looked like. Oh my God, that's really weird. Let me zoom out a little bit. Huh, interesting, huh? Who would have thought? So this graph is kind of cool. It doesn't pass the vertical line test. It's not a function of x, but we certainly could at any point, you know, like this really weird loop on it, you know, pick a point, draw a tangent line to that point and go, hey, so I'm just going to pick a point. Hey, there's a point, draw a tangent line. What's his slope? Well, if you get the coordinates of that point, which it looks like it's going to be what, like negative 7, 4 or something. I'm just kind of eyeballing it. If you plug the coordinates negative 7, 4 into that dy dx formula we just got, which is pretty hellacious, that would give you the slope of that tangent line that I just drew to that graph. Okay, fine. Now, how would a Calc 3 person do this? Well, it's totally different. So first, let me derive the formula to get the dy dx in it, so that we won't have to do it the Calc 1 way. So here's how you do it. You first get your equation, the implicit function, written where everything's on one side and zeros on the other. Okay, fine. Then what? You use the chain rule to take the derivative of both sides of this equation, where w is equal to this big F function. Big F is a function of two variables because it's got x's and y's in it. Okay. So when you take the derivative of the right-hand side, it's easy because the derivative of 0 is just 0. But when you take the derivative of the left-hand side using the chain rule, you're going to have the partial of big F with respect to x times dx dx. I know that sounds kind of weird, but because you've got big F here, and big F is a function of x and y, but both of these guys are, you could kind of think of functions of x here. It's a weird tree diagram. So you go down the first branch, and there's your fx times dx dx, which is just 1. And then you add to that the partial of f with respect to y times this branch, which would be dy dx. Okay. And then, like I said, the derivative of the right-hand side is 0 because, you know, derivative of 0 is always 0. Now, what do? You solve this equation for what? You solve it for dy dx. Oh, by the way, you know that dw dx is 0. That's there talking about the right-hand side because it equals 0. So when they solve for dy dx, this dx dx just turns into a 1. You first subtract fx from both sides, okay? And then you divide both sides by the partial of f with respect to y, and you get that dy dx is going to be equal to didn't want that to happen, negative fx, so negative the partial of big F with respect to x, divided by the partial of big F with respect to y. It starts by this because this is your key. So let's do that last example all over again. We already know what the answer is. We got from Calc 1 approach that dy dx is equal to this weird looking quotient, negative 2x minus 4y divided by 3y squared plus 2y plus 4x minus 5. But let's do it the other way before I do the theorem. So first, step 1, we need the form, get it into the form where everything's on one side and zero's on the other. Okay?
Hey, Professor, I think ours is different because we have a different implicit function. Like, for example, 8. I don't know if you have an example 8 on here.
I do have an example 8, but we haven't gotten there yet.
Okay, my bad. Because this one said example 7 for ours.
Okay. I apologize for the, so you're telling me that this one that I just did is example 7? Right here?
Yeah.
Okay. All right, well, let's just go with it. Is that okay?
Yeah, I was just kind of confused.
Is it the same function?
Yeah.
Okay, so a little bit off there. So we're going to do the previous example all over again, if you don't mind. So I'm going to get everything on one side and 0 on the other. So how do I do that? Well, that's just algebra, you know, and it doesn't matter which side you want to move things to, your choice. You want to move everything to the right-hand side and get 0 on the left, or do you want to move everything to the left-hand side and get 0 on the right? I don't mind whichever way works for you. So how about I just move everything to the left? So I'll keep the stuff that's over there already and move the other 3 guys over to the left. And folks, I want you to get that the importance of this problem that I'm doing right now and this step where you move everything to one side and 0 on the other is going to come up again and again and again over the next 3 weeks when you're working with certain types of problems. So if you skip this all important step and somehow magically get the right answer, you will not receive full points.
Is it supposed to be plus x squared?
Yes, thank you.
Mm-hmm.
So you need to get everything over here. Why? Because this is a different representation of the function. It's implicit. The mess that you see on the left, because it has x's and y's and numbers in it and all sorts of junk, this is considered a function of 2 variables. So we rename it big F, x comma y. And it equals 0. Okay. So using the formula dy dx, that's going to be negative fx over fy. How do I know that? Well, if you were watching me do that last little derivation, it's because of this derivation right here. This is a fact. Commit it to memory. So now we're going to do partials. So don't forget this minus. I usually just keep it out in front so I don't forget it. You can move it, you know, in the front. Let's get fx up here. So what is fx? You're going to look at your big F. That's this entire mess that you see on the left-hand side. And you are going to go, what's the partial of that with respect to x? So if I put on my special set of glasses and I treat y as a constant and differentiate with respect to x, what is that going to give me? So what is the derivative of y cubed with respect to x? Anybody want to be
0.
brave?
0.
Yeah, 0. Plus, what's the derivative of y squared with respect to x?
0.
plus, now this one's not going to be 0. What's the derivative of 4xy? But with respect to
y.
x. 4y, yeah. And of course, we know the minus 1 goes to 0. How about minus 5y with respect to x?
0.
And how about x squared with respect to x?
2x.
Beautiful. And you don't have to write the zeros, so you just get rid of them and we're done. All right, now the denominator is, we're going to start all over again and we're going to take the derivative of this big f function, but with respect to y now. So put on a different set of glasses where all of the instances of x look like a constant, some pure number. Okay, here we go. What is the derivative of y cubed with respect to y?
3y squared.
How about y squared?
2y.
How about 4xy?
4x.
And minus 1, 0. How about minus 5y with respect to y?
It's 5.
With the minus. And how about x squared with respect to y?
0.
Good. So we're done. Now the question is, does this match the answer that we got on the previous page? Check it. It does, because this minus, if you distribute it over the numerator terms, it will give you the minus 5y minus 2x, and then you've got that same denominator. And so it worked. Aren't you impressed? Happy face? Everybody in the room should be saying the following right now. Wow.
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 Is that something else? Now, don't go showing a calculus.
Wow.
This. Yeah, wow. If you have a friend in Calc 1, don't show them this cute little trick. It'll mess them up. They don't need to know partial derivatives yet, okay? They're already trying to get their minds around regular derivatives, okay? But for us, it's kind of like, hey, cool. That's a lot easier than doing it the Calculus 1 way, right? Wow. Okay, now let's fill in this theorem. So we already did this. You now know this is really true. And it turns out that if you use a similar procedure on a function of 3 variables equaling 0, and you need to find the slope of the surface in the direction of the positive x-axis, that's dz dx, partial. And if you need the slope of the surface in the positive y-axis direction, dz dy, you can use these two handy formulas. But you need to do step 1. I need to see it on your paper. If I don't go, I did it in my head. Not going to buy it. So we can do work with implicit functions of x and y here in Calc 3. So what am I saying? So let's just, before I even do this last example here, let me just cut to a quick page. So what do we know so far in our study here? So far, you have been given an explicit function of x and y, which you'll have the pleasure of doing on this week's quiz also. So you'll be, you're given z is equal to f x comma y. As an example, I'll just make something up. Z equals 3x squared minus 5y squared plus sine xy. I don't know. That's plus 2. There you go. There is a function of x and y, and it's explicit. Why is it explicit? Because z is on one side of the equation, and the x's and y's and all the other numbers are on the right. That's explicit. So what's implicit? Well, implicit is where you can't solve it for z because it's just too hard. There's no way you could isolate the z and get all the x's, y's, and the other junk on the other side. Forget it. Now, once you have explicit form, what's nice about explicit form is, if somebody goes, hey, go get dz dx, you know how to do that, which you could also, other notation fx, or somebody said, hey, go get dz dy, you go, hey, no problem. I know how to do partial derivatives, no problem. Easy. And I'll put like easy. You'll be doing that in this week's quiz. But what if you're given implicit form? So check out this baby. This is a pretty hardcore looking equation. That's not easily solvable for Z. I mean, good luck. Good luck trying to totally solve that for Z. Z is showing up in a lot of different places. You got a Z, you got a Z cubed there, you got a Z over here, and you'd have a tough time completely isolating that Z. But what if somebody said, hey, that does give a nice surface, and I still want to know what the ZDX is, you know, that slope in the X direction, and I still want to know about the slope in the Y direction. Like I still want them, just like we did in Calc 1, where when we had this implicit function of X, which got us that weird looking curve, we still wanted to talk about taking, you know, a point and drawing a tangent line to it and saying, what's the slope? We still wanted to be able to do that. So we still want to be able to do that with implicit functions of X and Y. And so while I'm here in the graphing zone here, let's graph that surface that's given as an implicit function of X and Y. Heck, I don't even know what it looks like. 3x squared, yeah. Z, what else do we got here? Plus 2z cubed, yeah, minus 5 equals x squared, y squared. And you could do this in GeoGebra, I'm sure, 3yz. I have no idea what it looks like. Oh, wow, that's kind of pretty. That's a nice looking surface, isn't it? Pretty. I can make it different colors. No, that's not that good. You can't do candy stripes because my software, if you give it as an implicit function, you don't have as many color choices, which is kind of sad. Explicit functions, you get all the other choices for colors. So what if somebody said, hey, you know, if this is a nice surface describing a mountain and you wanted to ski in the positive X direction, what's the slope? You know, so they're still wanting the slopes. Okay, fine. So let's go use our theorem that allows us to figure out what those slopes are. But we got to do step one. You got to get everything on one side and 0 on the other. And then you rename all that junk on the left, big F. And once you have big F, then you can get these ZDX because you'll have negative big Fx divided by big Fz. And then we can get dZdy because it'll be negative big Fy divided by big Fz. Okay, so here we go. Step one, we need a function of 3 variables, big F, all the X's, Y's, and Z's on one side of the equation. Which side? Doesn't matter for now. I'm just going to move everything to the left. And have it where it's all equal to 0. And so this big old function on the left-hand side is big F, and he's a function of X, Y, and Z. So the notation parentheses X, comma, Y, comma, Z. And somebody looking at it goes, oh yeah, that's a function of X, Y, and Z. And this actually describes a level surface, because remember, level surfaces, you set your function of 3 variables equal to a constant, where the constant happens to be 0. So this is a level surface for a function of 3 variables. So now let's go get dZdx. Okay, so dZdx is negative big Fx divided by big Fz. Here we go. Negative. Let's take the derivative of this huge mess with respect to x. That means you have to hold y and z constant. So that means put on a special set of glasses and treat y and z as pure numbers and take derivatives with respect to x. Here we go. The derivative of 3x squared z with respect to x is 6xz. The derivative of 2z cubed with respect to x, 0, minus 5, 0. The minus x squared y squared with respect to x is minus 2x y squared. And the derivative of the last term, 3yz, with respect to x is 0. I'm done. Now let's do the denominator. Take the partial of big F all over again, but with respect to z. That means you're going to put on a different set of glasses, and it's going to look like x and y are pure numbers. Okay, differentiate with respect to z. Derivative of 3x squared z with respect to z. 3x squared plus 2z cubed's derivative with respect to z. 6z squared. The minus 5 goes to 0. The minus x squared y squared, that goes to 0 because you're differentiating with respect to z. Derivative of 3yz with respect to z, 3y. And there you go. There's your dz dx for that function. Yay! And give you a slope. Let's go get dz dy now. The other implicit functions partial here, the dz dy, using the theorem, is negative fy over fz. Now, the good thing that's in common with both of these partials is the denominator is the same. So I'm just going to copy down the same denominator that I got from the dz dx. That's a little trick for you. Don't reinvent the wheel. You already got your fz. Don't take it over again. And so we only have to worry about the fy. I like to put my negative way out front so I don't forget it. A common student error is to forget that negative altogether. Don't lose your points from missing that negative, because usually I'm really gentle with you if you just screw up and have a negative wrong, but I'm not so nice here. Well, how come? Because it's part of the formula. So if you forget your negatives this time, lots of points will be taken away. So don't blow it. I put your negative out here. And if you want to, you can always distribute the negative over the numerator if you like. That's fine also, but I usually just keep it out front so I don't blow it. Okay, so now I'm going to retake the partial of that big F, but this time with respect to y. So the derivative of the first term, 3x squared z, with respect to y, 0. Derivative of second term, 0. Derivative of third term, 0. Wait, the derivative of minus x squared y squared is minus 2x squared y. That did not go to 0. And the derivative of 3yz with respect to y is 3z. Okay, and we're done. And if you want to distribute this negative over the numerator terms, you can. That would be positive 2x squared y minus 3z all over that denominator. I'm just going to copy them down. And that would be your partial of z with respect to y. Okay? Now, the last little piece that they want us to do, which I didn't give myself enough room, what is the slope of the graph of the equation in the x direction at the point -1, 0, 1? Well, that would just be evaluating your dz dx at the point -1, 0, 1. And there's just a lot of substitution you're going to do. So you're just going to take your dz dx and you're going to start substituting -1 in place of x and 1 in place of y, and 0 in place of y, and z gets a 1, right? Okay, here we go. And after you do all the math, it should come out to be 2/3, okay? Did that right, I hope?